So we are in lecture 6 of unit 1. Today's title is Random Variables, Introduction to Random Variables. Okay. So the random variables are discussed in more detail in the next chapter. So this first unit just gives a small introduction to random variables. Okay, so we'll see what are random variables. We'll see what is the concept of a random variable and what are the conditions for a function to be a random variable. Okay, basically a random variable is a function, so we'll see what are the conditions that any function should satisfy to qualify itself as a random variable. And then we'll see some solved examples in classification of random variables. Okay, so this is the outline of today's session. Okay. So now moving on to the topic. So we'll just consider an experiment, an example experiment. Okay. So consider an experiment where you have to pick a random student. Okay. So you have been given a class, and from that class you have to pick a random student. Okay. So this is a random experiment. Okay. So the outcome of this experiment is one particular student. Okay. So I have represented all the outcomes inside this oval, right? Inside the circle or oval, whatever shape. So I have represented all the outcomes. Okay. So usually, whatever till now, whatever we have seen, the outcomes are sometimes quantitative and sometimes only qualitative. That is, the outcome of an experiment is sometimes just a descriptive outcome, right? So we can say taking out a red ball. Okay, so the red defines the quality of a particular outcome, right? So we can say whether it is raining or not. Okay, so the whether it is cool or hot, whether the outside ambience is cool or hot. These are all qualitative descriptions, right? So we are just giving the quality of a particular outcome. Okay, so in some experiments, what we have is a quantitative outcome, right? So, for example, if you take the case of tossing a, rolling a die, right? In that, the outcome is a quantitative outcome. So, rolling a die, so there is a number that is showing up, right? So, we have 1, 2, or up to 6, whatever number, that is the number that is showing up. So, that is a quantitative outcome. Okay. So, if we want to do more practical work in probability theory, it is more useful to define every outcome in a quantitative way. Okay, so that is why we introduce a concept called a random variable. Okay, so for example, take this example of choosing a random student. Okay, so choosing a student is a qualitative outcome, right? So particular student, maybe the student has a name, say Ram or some say Anthony or something like that. So we have a particular student who has a name, and then we are just selecting him, right? So that is a qualitative outcome. Now we can define a process, or we can design a set of rules to be followed, whereby we can assign a particular number to the outcome of this random experiment. Okay, so take for example the same experiment where we are picking a student randomly from a class. We are picking up a student. Okay, so this is the student I have chosen. Okay, so using that, I can measure his height, and I can qualify, or I can quantify the outcome by the height of the student. Okay, so assume that we are naming the students as S1, S2, S3, S4, etc. to Sn. Okay, so I have taken a student S1 and I'm measuring his height, and then I'm recording his height in inches, 82.3. Right. Again, I'm choosing a student S2, measuring his height and recording his height, 86.4. Okay, so similarly, I'm taking another student S4, S3. So different heights are mentioned here, right? So what here actually we are doing is we are associating each student with a particular real number, right? So this association, or the rules which we follow to arrive at this number, okay, so those are collectively called as random variable. Okay, so the name random variable is a little bit confusing. Okay, so we are saying that it is a random and it is variable. Okay, so it will be a little bit confusing, but simply stated, it is just a set of rules, okay, which we follow to assign a particular number. Okay, so previously we have followed some set of rules to assign a probability. Okay, so that is different thing. So here what we are doing is the outcome itself is assigned a number. Okay, it is not the probability of that outcome, it is just a number associated with an outcome. Okay, so we are following a set of rules to assign those numbers. So those set of rules are what is known as random variables. Okay, so basically what we are doing is we are mapping all the outcomes of this sample space S to a real number line. Okay, so since mapping is in the context of functions, right? So mapping means we have we have one set of values. So all those values go into a particular function, and then that function generates some other set of values. Okay, so that is what is called a mapping. Okay, so here we whatever height we have measured, so that measurement operation that I have represented using the capital H, right? So H of S. So what it means is H is the set of rules that we are following to arrive at the numbers that are listed on the line. Okay, so the set of rules are called the random variable. So here the capital H represents the random variable. Okay, so the random variable is a function of the small s, which represents individual outcomes of this experiment of picking a student. Okay, so the small s represents at any point of time, the small s represents any one of the student among the class, among all the students in the class, right? So we have a function which maps points in the sample space to points on the real line. Okay, that is the real number line. Okay, so that function is what is known as the random variable. Okay, we can think of it as a set of rules, right? Or sometimes it will be mathematically defined, sometimes it will be the set of rules will be just qualitatively defined. Okay, so we'll see some examples to understand what is random variables in more detail. Okay, okay. Similarly, okay, I'll go back to the next slide and then come back to the slide again. Okay, so okay, first we'll discuss in this slide itself. So suppose we have the same set of students. Okay, so now instead of measuring the height, I give you another rule, like measure the weight of the student and plot it in the number line. Okay, so that is a different set of rules, right? So my first rule was measure the height of the student and and assign that number on the number line. So that is one first set of rules. So I'm giving you a second set of rules where I'm asking you to measure the weight of each student. Okay, again, the weight is a random variable. So S1 will have a particular weight. So student S2 will have another weight. Okay, so again, weight itself is a random variable. Okay, now instead of measuring the height in inches, I'm asking you to measure it in centimeters. Okay, so what will you do? So we can define another function h dash of s, which is equal to 2.5 times h of s. Okay, so now if you do this operation, all the heights you will be getting in centimeters. Right? So again, that again is a different random variable. Okay, so we have w of s, which is weight of all the students. That is one particular random variable. We have h dash of s, which is again another random variable. What is the difference between the h of s, w of s, and this h dash of s? So can you observe any difference between h of s, w of s? So these two are similar kind, right? H of s and w of s are similar, but this h dash of s is somewhat different. So what is the difference? Just I'll use my highlighter. Okay, so this w of s and h of s, these are direct functions of the sample space, right? So they are taking directly values from the sample space, but this h dash of s is a function of another random variable h of s, right? So it can be a function of some f of h. Okay, so there are some random variables which are direct functions of the sample space. So some random variables are functions of other random variables, right? So like this, we can create numerous random variables. Okay, so any number of random variables can be created either directly from the sample space or as functions of other random variables. Okay, so summarizing whatever we saw in this. So this gives us height in centimeters. Okay. So these are the things we summarized using the previous slide. So the random variable is nothing but a set of rules which are followed for assigning a value to outcomes of a random experiment. Okay. So it is an assignment of a value, which is a real number, to every possible outcome. Okay. So mathematically, it is a function from sample space S to the real numbers. So it can be the mapping can be either a discrete mapping or a continuous mapping. So we'll see what are these discrete mappings and continuous mappings in the upcoming examples. Okay. So one important point you should remember is the naming of a random variable is actually it is confusing, right? So the random variable is neither random nor it is a variable. Okay. So given a particular outcome, you have a fixed number. Okay. So here you are giving a number to a particular outcome, right? So once the outcome is fixed, your number is fixed. So it is not a variable. Okay. So the name is misleading, but somehow that name has stuck. So the random variable name has stuck. It is not neither random, right? So it is neither random nor a variable, but its name has random variable. Okay? So you should not confuse random variable to be a variable, like it is always varying or it is random. Okay, so it is a number that is assigned to a particular outcome. That is all is the meaning of random variable. Okay. Okay, so as we have seen, we can have several random variables defined on the same sample space. So in the previous example, we saw how we can associate height with the sample space, how we can associate weight with the sample space. Okay, even we can associate some other random variable which is a product of height and the weight, right? So we saw we can even form another random variable as a function of the existing random variables. Okay, so given a particular sample space, we can have several random variables. So that is what is given in the sentence. Okay, and one important point to note here is about the notation. Okay, so any random variable, it is shown by a capital X. Okay, so I mean any capital alphabet. Okay, so here I am using the alphabet X. So any random variable will be denoted by a capital letter. So the numerical value that a particular random variable takes for a particular outcome, that will be shown as a small letter, okay, small alphabet. So this is the notation that is followed. So the notation is a simple thing, but when once we are clear about the notation, it will solve a lot of problems later. Okay, so it will not it will be avoiding many problems later. So it is advisable to be clear with the notation. Okay. So the random variable itself is denoted by a capital letter, and the numerical value it takes for a particular outcome, that is denoted by a small letter. Okay, so again, I'm just giving it as a function from this sample space to the set of outcomes to the set of real numbers. Okay, so the capital R denotes the real number, and this numerical value x is a real number. So it is an element of the set of real numbers. Okay. So now we come to the conditions for a function to be a random variable. Okay. So what we have just seen is that a random variable is nothing but a function. Okay, function is nothing but which maps one set of values which are called the domain to the range, right? So the set of values that can go that we can substitute into a function, they are called the domain of the function, and the set of values that are result of the function, those are called the range of the function, right? So it is a mapping from here to here. So x is a mapping. The random variable x is a mapping from the set of outcomes of the random experiment to the set of real numbers. So again, this is also a mapping. Okay. So what we are showing here is here. I'll just change my highlighter. So here, if you see, so these are the points in the sample space. There is this one outcome. There is another outcome. This is another outcome. So this is another outcome. So here 1 point. So here 2 points of the sample space are getting mapped to 1 point in the real number into the set of real numbers. Okay. So this is a valid random variable. Okay. So here this x is a valid random variable. Okay. So here what happens? A particular outcome is mapped to two different values. Okay. So this particular outcome of the random experiment is mapped to two numbers here. Okay. So this cannot be a random variable. Okay. So this thing cannot be random variable. So that is why we say it should not be multi-valued. Okay. So a function defining the random variable should not be multi-valued. So by multi-valued, what we mean is a single outcome in the sample space should not be mapped to two different numbers. Okay. So here one number and here one number. So there are two different numbers. So this case is not useful practically. So this random variable is not at all useful. Okay. So such random variables are not at all created. Okay. So any random variable will associate only one unique real number to a particular outcome. Okay. So two outcomes can map to a single real number. Okay. So this is a valid thing. But one single outcome cannot be mapped to two different real numbers. So that is what we call it as multi-valued. It should not be multi-valued. Okay. So this is one particular rule or one particular condition. And another particular condition is the set which is defined by the values of the random variable less than a particular value x. Okay, less than a particular numerical value x. It shall be an event for any real number x. Okay, any real number small x. Okay, so what do we mean by this is, so once we have associated a real number with the set of with all the outcomes. So if we take any real number, so all the numbers less than that should also have a corresponding outcome in the sample space. Okay, so any number which we choose less than the small x is a given real number which has its associated outcome in the sample space. So all the numbers that are less than that number should also have some associated outcomes in the sample space. So that is the second rule. Okay, so the third rule is that, or the third condition is that the probabilities of the events, that is x equal to infinity and x is equal to minus infinity, should be 0. Okay, so the point to note here is that the random variable x itself it can take the values of infinity and minus infinity, but only requirement we are having on the random variable is that the probabilities of the events. Okay, so x equal to infinity, it might be corresponding to one particular outcome in the sample space, right? And x equal to minus infinity, it will correspond to another particular outcome in the sample space. Okay, only requirement is that the outcome should have a probability of 0. So both the outcomes should have probability of 0. Okay, so these are the three conditions for a function to be a random variable. Okay, so we can choose any function, but provided the function satisfies these three conditions. Okay, so we'll understand these conditions when we do more problems. Okay, so these are the conditions for a function to be a random variable. So moving on to the next slide. So we'll see some examples to understand the concept of random variable in a better way. Okay, so before we see examples, I just want to once again stress the different classifications of random variables. Okay, so a random variable can be a discrete random variable. Okay, so it can have only discrete values. Okay, so take for example in the real number line, we're just taking integer values. Okay, so if you consider our previous example, so for example here we are mentioning the heights in inches. Okay, so suppose I ask you in this rule, suppose I ask you to do one more, suppose I ask you to follow one more rule that you round up the height of the student to the nearest integer. Okay, so then what you will be getting? You will be getting just the integer part. Okay, so the 60.5 will become 61. So 71.35 will become 71. So 82.3 becomes just 82. 86.4 becomes just 86. Okay, so we'll be just associating some integer values with each student. Okay, so that kind of mapping, it is called a discrete random variable. Okay, so here what we are seeing is a continuous random variable. Okay, it can take any value in the number line. Okay? So discrete random variable just maps only discrete values in the real line to each outcome of a random experiment. So continuous random variable maps all the outcomes to continuous values, okay, in the real number line. So we can like discrete and continuous random variables, we can also have some mixed random variables where some values are discrete, some are continuous. Okay, so we'll see some examples to understand how we are defining, we are classifying some random variables as discrete, some as continuous, some as mixed random variables, etc. Okay. Yeah. So now I have given a particular example problem where given a sample space for an experiment. So here the sample space itself is already in a quantitative form, right? So since it is in the quantitative form, we can directly take the sample space itself as a random variable, okay, or we can define the functions given here. Okay, so I've given 4 different functions of the sample space. Okay, so we want to find out what are the possible values of the random variable x. Okay, so can you give the set of values? So first given x of s equal to 2s. So what are the possible values of x?
0,
0, 2,
Yeah.
5,
So it
12.
is just,
5, 12.
yeah, good. So it is 0, 2, 5, 12. Yeah. So these are the set of, yeah,
5,
good. Okay, so these are the set of values. So we have to note how we are denoting the set of values of x. Okay, so just so the notation plays an important role. So to avoid confusions, we have to use the proper notation. So you can see we are using a notation s of x. Okay, so we are not using x equal to. We are just using s of x. Okay, so all these small values inside this s of x. So these are denoted by small x. Okay, so these are denoted by small x. Okay, so s of x represents list of all possible values of the random variable x of s. Okay, so these are the set of values. Okay, so now can you give the set of values for this second x of s? So it is just a matter of substituting the values of s and then finding out, right? So what are the values for the second one? So 5s square minus 1. So you obviously plug in all the values.
minus 1, 4.
Minus 1, 4,
4,
30.25, 179.
179. Very good. So we are just plugging in all the values from s into the function x of s. Okay. So one more thing to note here is that the values of s are all discrete values, right? So as a result, we are also getting the sx, s suffix x. That set is also discrete. Okay. So what are the values for x of s in the third one? C is what is the set sx for the third one? That is cos pi s. So cos 0 is 1.
1.
So how many
Cos pi
1
minus
minus 1,
minus 1. 1 minus 1.
so 2.5 is 5 pi by 2. So again 6 pi.
0.
0.
Yeah. So
1,
here we have,
1 minus 1,
0,
0,
1.
1.
yeah, only, yeah. So the thing is we are listing out the set, right? So see what we are doing is we are listing out a set, right? So a set should not have repeated elements, right? So for this case, we have minus 1, 1, 0, and then again the last one is also coming as 1. So we don't repeat it. Okay. So we are just listing out all the possible values. So here we'll have only 3 different values. Okay. So here we are just having 3 different values, 1, minus 1, and 0. Okay. So what happens is 2 values from the sample space, they are mapping onto single value, right? So the one is the one value is mapped from 2 different outcomes. Okay, so and then the last one x of s equal to 1 by 1 minus 3s. So that again is a matter of just plugging in all the values. So for 0 it is 1, for the second value 1 it is minus 0.5. So similarly we can get other values. So whatever we have seen here is all a collection of discrete random variables. Okay, so all the x listed here, so all the x's listed here, so they all lead to discrete sets. So all the sets we are seeing here are discrete sets. Okay. So now in the next example we will see continuous sets. Okay, now take this example. So here we have a sample space which itself is a continuous sample space, right? So this is a different sample space. It is defined in a continuous. It is defined as a continuous set, right? So it is a set of all real numbers from -2 to 5. Okay. So now can you find out this? So here I have given the same list of x's. So only difference is our sample space. This is a continuous sample space, right? Okay. So now what are the results of? How will you list out? Okay. So now you have to concentrate on the notation for listing out the values of the random variable x. Okay. So here we will be using the small letter x. Okay. So Sx is the set of all x which are greater than -4 and less than 10. Okay. So here I am using the notation of small x. So in the previous discrete case, I was using just a set. I was just listing out all the elements of the set. So here I am using the notation of small x because small x is the symbol we use for all the elements of x, all possible values of numerical values of the random variable x. Okay, so can you list out the other sets? So in a similar fashion, can you list out for x of s is equal to 5 square minus 1? So starting value is -2. So here it will become 4. So it will be 19. So yeah, 19
19 to
to
124.
24.
here. Yeah, I think there is a mistake here. So it's yeah, actually here there is a mistake, right? Yeah. So just uh, change this one. So it is 19 to
Sir, -1. Okay, sir. Saripan, sir.
yeah, okay. It's from -1 to 124, correct? So -2 here is 4.
Sir, 0 means -1. 0.
When it is 0,
-1.
yeah, okay. So it is so this is the correct set of all the x values. Okay. So what is the next one? What is the set?
-1 to 1.
Yeah, it's from -1 to 1. Okay. So what about the next one? So here you have a peculiar x of s. Okay, so where the set of all possible values
-1 to 4.
-1 to. So here you have a function where it behaves in a peculiar way near the value of 1 by 3, right? So when s takes a value of 1 by 3, so what happens to this value? See, when s value equal to 1 by 3, this value becomes infinite, right? So at s equal to 1 by 3, this value becomes infinite. So how will you accommodate that infinite value while defining or while listing all possible values of random variable x? Okay. So what we do is, so we start from -2 and we reach up to 1 by 3. Okay. So from -2 to 1 by 3, when it is -2, it takes a value of, so it is 1 by 7, right? It takes a positive value of 1 by 7. So at 1 by 3, it takes a value of plus infinity, right? So at 1 by 3, when x equal to 1 by 3, it reaches plus infinity. Okay, so for s equal to a value which is slightly greater than 1 by 3. Okay, so 1 by 3 is say 0.33, right? So it is, I just denote it by 0.33, etc. So at this value, this x of s takes an infinite value, right? Positive infinity. So just take some value which is nearby 0.33, say 0.34. So substitute 0.34 for this s value. So it'll be getting a large negative number, right? So for values from -2 to 1 by 3, for values of s from -2 to 1 by 3, we have values which are moving from 1 by 7 to plus infinity, right? So similarly for values from slightly greater than 1 by 3, so 1 by 3 to 5. So how does it behave? It starts from minus infinity and it reaches a value of, so substitute 5 here.
Minus 1 by 14. Minus 1 by
So
14.
it reaches minus 1 by 14. Okay. So if you can visualize this, there is a slight. So this is a slightly different. Okay, so okay, I've listed it here. So x values are from minus infinity to minus 1 by 14, and another set of values which are from 1 by 7 to infinity. Okay. So we can list this in a, we can show this in a graph. Okay, so we can just put a graph and okay, so these are the values of s. Okay, so here there is a small mistake in the second graph. Okay. So what we are seeing here is the set of all values, right? So these are different kinds of set of possible values of random variables. Okay, so here we have values of s. These are the values of sx. So this is one set of values, and okay, actually this graph should be down here, so it should start from minus 1 by 14. So these are another set of values. Okay, so here we have two different set of values. So this is one set. So this set corresponds to -2 to 1 by 3. Okay, so this set of, actually this flat portion should be coming here. Okay, so there is a mistake in the graph. So here we have what is 1 by -1 by 14. Okay, so it should stop with this point. Okay, so actually the graph should be like this. It should flatten here. Okay, so not this. Okay, so it is an exponentially flattening graph. Okay, here it goes to minus. So this is the point we have 1 by 3. Okay, so along 1 by 3 it reaches to infinity. Again, for the next immediate higher value near 1 by 3, it reaches minus infinity. Okay, so here it is minus 1 by 14. Okay, so here we have two different set of values which are discontinuous. Right? So this is one particular set of value and this is another set of values. Okay, so these are different kinds of random variables which we saw in this example. Okay, so we'll be moving on to the next slide. Okay, so now we can classify the random variables. Okay, so you've been given some random variables, and you have to classify whether they are discrete or continuous or mixed random variables. So what about the first one? Is it a discrete or a continuous random variable? So set of all x such that it has values between -20 and -5. So it occupies all the points in the number line. So obviously it is a discrete random variable. sorry, it's a continuous random variable. Okay, so the second set, if you see, it takes on values, a separate value 10, and then it takes values from 12 to 14, all the continuous, all the real numbers. Yeah, it is a mixed random variable. So what about the third one? The third one, it is minus 10 for s greater than 2 and 5 for s less than 2, where s is from 1 to 6. Okay, on the real number,
Mixed.
is it mixed or discrete? Yeah, it is discrete because it takes only two values, minus 10 and 5. Okay, it doesn't take any other value. So it is a discrete random variable. So what about the last one? Obviously, it is discrete because
Discrete.
it just takes some discrete values,
Discrete.
4, 3.1, 1, and minus 2. Okay, so this we come to the end of this session. So this is a small random variable concept. So we'll be seeing more detail about random variables in the next unit. Okay, so the next unit deals with the operations on random variables. Okay, so the main important things we'll be studying is, first we'll be having some standard random variables, and then for each of those random variables we'll be having some operations called expectation. Okay, so yeah, so this session just introduces the concept of random variables. So any doubts in the concept of random variables? So what is basically a random variable is a set of rules or a function by which we assign a particular number to a particular outcome of a sample space. Okay, so the rule can result in a discrete set of values, or it can result in continuous set of values, and the rule should follow certain conditions. So that is what we saw in this session. So just a minute, I'll take attendance. So there are 54. I'll just take a snapshot. So, so with this we have come to the end of the first unit. Okay, so from the next class we'll be seeing the second unit. So we'll be starting a fresh unit. We'll see operations on random variables. Okay, so if we want to just have a revision of quick revision of whatever we saw in the first unit. Uh, okay, so in the first unit we just saw what is probability. Okay, so how to model uncertain situations. And then we, through the use of set theory, we introduced what is known as the probability axioms. Okay, so we saw what are the three steps in modeling uncertainty. First step is defining a sample space. The second step is defining some events. Okay, and then the third step is assigning some probabilities to events following certain axioms. Okay, so these are the three steps in uh, modeling a random experiment or modeling some uncertain situations. Okay. And then we saw about sample spaces. What are the different kinds of sample spaces? So sample spaces can be discrete or it can be continuous. Okay, so and then we saw what how to interpret the results of probability. Okay, so what does the number mean? What does the probability number mean? Okay, so sometimes it is the frequency of events. It's the relative frequency of events. So out of all the trials that we conduct, how many trials result in our favorable outcome? Okay, so that is the meaning of relative frequency, meaning of probability. Okay, and then we saw definitions like conditional probability. What is a conditional probability? Okay, and then we saw what is Bayes rule. Okay, so using conditional probability, we were able to model some experiments. Okay, and from the results of those experiments, we were from the effect of the experiment, we were able to find out which cause will be most probable. That was through the use of Bayes rule. Okay, and then we saw what is total in while defining Bayes rule. We saw what is total probability. Okay, so total probability is the probability. It's the probability of all the ways through which a particular event can occur. Okay, particular outcome can occur. Okay, and then we saw what are independent events, and then we saw independence for two events as well as for multiple events. So how to define independence or how to check for independence of events just for two events and for multiple events. Okay, and then we saw what is joint probability, and we saw, okay, so finally we saw what is a random variable. Okay, so the concept of random variable is the next step in probability theory. Okay, so initially we were just concerned with outcomes and probabilities of those outcomes. So now we'll be dealing with random variables where we are assigning some numbers to those outcomes, and we'll be only dealing with numbers. Okay. So this is just a brief overview of the first unit. So, so the second unit will be the distribution and density functions and operations on one random variable. Okay, so from the next class, we'll be seeing the second unit. And regarding your assignment, okay, at the end of first unit, you'll be requiring to do an assignment. So I'll be giving you the assignment in a day or two. Okay, so maybe within 2 days, I'll be giving you assignment. And there are also two quizzes pending, right? The quiz for the lecture 5 and lecture 6. This lecture and the previous one quizzes are pending. So I suppose you have already attempted the yesterday's quiz. So yesterday I gave you one new quiz. I hope you are attending that. And if you have any doubts, you can either put those doubts in the class stream or you can mail me individually. Okay. So use my college mail ID to ask any doubts. Okay. And then okay. So this is what I want to tell you today. Okay. So with this, we'll be closing our session now. So taken the attendance, you can leave.